mode control changes the system dynamics by employing a discontinuous control system. So here you will find that which is known as classical sliding mode control or first order sliding mode control, where we will employ a discontinuous control signal. This approach has been well developed and extensively used in theoretical research and practical engineering design. You will find that several research papers have been published in the field of application of sliding mode control as well as the theoretical development of sliding mode control. It has been also successfully employed to solve various control problems in combination with other control approaches. Means it has a capability to combine the other control strategies with the sliding mode control to have the more or greater benefit. The sliding mode control method consists of two steps. That has to be remembered at the beginning. Whenever we are designing the sliding mode control for a given system, always we have to perform the two steps. First step is to design the sliding manifold. What do you mean by the sliding manifold? The design of a sliding surface such that the system considered possesses the desired performance when it is restricted to the surface. 1 second. Yeah. So now sliding. What is the sliding use of sliding manifold? Now, how we will design the sliding manifold. Sometimes I used to call this objective function. So first you have to see what is the objective of your controller design, and that objective functions will give you the hint how to design the sliding manifold. In this lecture, obviously, I'm going to discuss that one. The next part will be the control law, design of control law, the design of a variable structure control which drives the system trajectory to the sliding surface in finite time and maintains a sliding motion on it thereafter. So we have to design a discontinuous control for the classical sliding mode control that it will drive the system trajectory to the sliding surface in finite time, or whatever the sliding manifold you have designed, it will reach to the sliding manifold in finite time, and it maintains the sliding motion on it. Means once the system reach to the system trajectory is reached to the sliding manifold, it slides asymptotically towards the origin. So this is the strategy. Now I will discuss some one example here to understand the sliding mode control design, what I told. So for the illustration purpose, a single dimensional motion of a unit mass is considered. Suppose here a mass has been considered, and we are applying a force U. Fine. The state variable description is easily obtained by introducing the variable for the position and the velocity. So let us say that x1 is a state variable which is position, and x2 is the velocity, that is x1 dot. So now if we want to describe the dynamics of the system, which can be represented by the two-state equation where it is x1 dot equal to x2 and x2 dot equal to u plus f. So here F is representing the disturbance which may comprise the dry and viscous friction as well as any other unknown resistance forces. So exactly we are not knowing what the disturbance is this, but we know the bound of the disturbance, that is F modulus of F x1 x2 t, which is less than equal to L. L is the maximum bound of the disturbance that is greater than 0. Now this system is given to you, and what the control problem has been asked. The problem is to design a feedback control law U, which will be the function of the states x1 and x2 that drives the mass to the origin asymptotically. Means we want that this position and the velocity is going to settle at origin, that as the time tends to infinity. So this is our control objective, which is written again, that in other words the control U, which is a function of x1 and x2, is supposed to drive the state variables to 0, that is as t tends to infinity, x1 and x2 both must go to 0. This apparently simple control problem is a challenging one, since asymptotic convergence is to be achieved in the presence of the unknown disturbance, that is F. So suppose we will try to implement or try to design a state feedback control law, and we will see that whether this problem can be solved using sliding mode control, the state feedback control or not. So that's why, for instance, a linear state feedback control law is taken. That is, here one minus sign I have missed. It will be minus K1 X1, that is minus K2 into X2, where K1, K2 are the gains, and that will be chosen suitably. And first we have assumed that, so suppose there is no disturbance. We have first assumed that we have no disturbance, and we have chosen the K is equal to 3 and K1 equal to 3, K2 equal to 4, and we have taken the initial condition 1 and minus 2, and with this gain we have tried to plot the system trajectories by assuming the disturbance is equal to 0, and this is the plot we can see, where we can see both the states are converging to the origin asymptotically. So this controller, when there is no disturbance, it is means the state feedback controller is working fine. But if we will consider now the disturbance is sin 2t with this gain K1 equal to 3 and K2 equal to 4, we can observe that no longer the system states are going to converge to the origin. Instead of that, it is going to evolve within a bound, that is omega, and bound of the settlement will depends definitely on the magnitude of the disturbance. So now the question is that whether the formulated control problem can be addressed using only knowledge of the bounds of the unknown disturbance or not. So further we want to improve that even if this disturbance is present, the system will go, system trajectories will settle to 0 or origin as time t tends to infinity. That we want to do only by knowing the maximum bound of the disturbance. So to do that one, now we will design the sliding mode control. Now suppose if we are able to design a control law such that the system is the compensated dynamics of the system is represented by this equation, that is x1 dot plus c into x1 equal to 0. Means suppose we have a system, already I told that it is a second order system. Okay, now after applying control, if we have a compensated dynamics which is look like equation number 4, that is x1 dot equal to c into x1 equal to 0, then can we able to fulfill our objective? Let us verify that one. So we know that from the assumption that the x1 dot t is equal to x2 t. So now if we solve this equation, then we are finding that x1t will be simply x10 into e to the power minus ct, and x2t will be the x1 dot, that will be the derivative of this one. So if if we will select a c greater than 0, then we are finding that x1t and x2t both are going to be 0 asymptotically. It means that by a control, if we achieve a compensated dynamics like equation number 4, then our control objective is fulfilled. Now the question is that how to achieve this compensated dynamics? That is the important question. Now it has been asked. So how could this compensated dynamics be achieved? So now we will call this compensated dynamics as sigma. That is sigma equal to x2 plus c into x1, which is we can see that it is a function of states x1 and x2. So if we want to construct the sigma, we require the information of the states x1 and x2. Okay, and we have observed that somehow with the control, if we make sigma equal to 0, then both the states will converge to 0. So now in the presence of disturbance, now our objective is that how to make this sigma equal to 0 in finite time. Means we want to make this sigma equal to 0, means we want to design a control such that we can make sigma equal to 0 in finite time. So let us see the dynamics of sigma, how the sigma is going to evolve with respect to time, and then only we can stabilize, or we can make sigma equal to 0 in finite time. So to do that one, we will differentiate this sigma once. So if we differentiate this sigma, then we are finding that u is going to appear. So now we can design a u in such a way that we can make sigma and sigma dot both equal to 0 in finite time. So now how we can design u? That can be designed with the help of Lyapunov function. Suppose if we take a Lyapunov function v equal to half sigma square, and if we able to prove that the derivative of v, that is with respect to time, is less than equal to minus alpha v to the power half, then we can say that the system is globally finite time stable, because here we have to make sigma and sigma dot 0 in finite time. So let us so it has been shown that if we will choose, or if we able to prove that dv the derivative of time derivative of v is less than equal to minus alpha v to the power half, then always we can calculate a time by which we can reach to the sliding surface, or means here sigma equal to 0. So now that's why here, to find out the stability, v equal to half sigma square, so we have calculated v dot. If we will calculate v dot, it will be sigma into sigma dot, and sigma dot is already computed. What is the sigma dot already computed? This is the expression 8 is the sigma dot, which we will substitute here. So if we will substitute here, then we are finding that v dot is less than equal to mod of sigma into L plus rho into nu, where actually we have assumed that a control law u equal to minus c into x2 plus nu. Now what will be nu, such that we can easily show that v dot will be negative semi-definite. So now if we will assume that a nu equal to minus rho sine of sigma, then we are finding that v dot will be minus rho or minus sigma mod of sigma is equal to rho minus L. So here it is very clear that if we select the gain of the sine sigma rho is greater than the L, where the L is the maximum bound of the disturbance, then we can prove that definitely the v dot is going to be less than equal to 0, and we have found that rho must be selected L equal to alpha by root 2. And if we select the gain of the controller like this, then the final control law u will be c minus x2. This is the linear part which is going to cancel out this c into x2 part, and minus rho into sine of sigma. If we have a control law like this, then definitely we can stabilize the system, or we can guarantee that sigma and sigma dot both are going to be 0 in finite time. So now some of the things we will define now. The variable 7, that is sigma, is called the sliding variable, and the equation 4 and 7 rewritten in the form of sigma equal to x2 plus c into x1 corresponds to a straight line in the state space of the system, are referred to as sliding surface. So basically we want to reach to that sliding surface, and the condition sigma dot, which is less than equal to minus alpha by root 2 mod of sigma, is often known as reachability condition. Okay, and the control u, what we have designed here, okay, that drives the system states x1 and x2 to the sliding surface in finite time tr and keeps them on the sliding surface thereafter in the presence of the bounded disturbance f, is called the sliding mode controller, and an ideal sliding mode is to be taking place in the system 1 for t greater than tr. And with these parameters, again the same system has been simulated, where we can see that the sliding variable sigma is going to be 0, okay, and both the states are converging to 0 asymptotically, even if the system is affected by the disturbance, that is sine 2t, and where we can see the reaching phase and the sliding phase. So from here, this phase is the reaching phase, and then the sliding, this phase is the sliding phase, where we can see that system trajectories are slides towards zero asymptotically. So this is the phase portrait where we can see that reaching phase and the sliding phase. Now, this is a particular example of a second order system we have taken, but in general, what will be the designing methodology? So now that's why we have taken a generalized system, and then we have tried to design the sliding mode for this system. Suppose any system we have taken, that is x dot equal to ax plus b into fx comma t, and here x is belongs to Rn, n number of state vectors are there, we have m number of control input, and now we are assuming that the rank is rank of b equal to m, and the pair ab is controllable, and the function f is bounded, and it is a continuous function. Now, to design this, now what is our control objective? The control objective is that to stabilize the system. Means we want that that as the limit that is limit t, our objective is that limit t tends to infinity, x of t must be equal to 0. And what is the challenge? Challenge is that even we have to ensure the asymptotic stability in the presence of this disturbance. Previously, we have seen that in the previous lecture, where we have shown you that using the PI or PID and the state feedback controller, if the disturbance is present, the maximum or as maximum we can ensure that ultimately ultimately boundedness of the system, but the asymptotic stability we cannot ensure in the presence of the disturbance. But now we are going to show that using sliding mode control strategy, it is possible to achieve the asymptotic stability of a given system, even if the system is affected by the matched disturbances. So to do that one, what we want to do, we want to represent the system 1 in the coordinate of eta and zeta. So we want to transform, we want to take the help of transformation matrix T, and such that we can represent the system in the coordinate of eta and zeta, and it is a special system representation which is known as the regular form. So now if we can find out a suitable matrix T such that we can represent the above original system in the form of in the eta and zeta coordinate, where we can see that the zeta dynamics only having the disturbance and the control input, and eta dynamics is free from the input and disturbances. So this form is known as regular form. So this is the regular form. So we always, if the AB pair is controllable, then always we can find out a suitable T matrix by which we can transform the given system in the regular form. And the speciality is that if you have the m number of control input, the dynamics of zeta will be belongs to m, and the eta will be the n minus m dynamics. Okay, so now if we are dealing with a single input case, so then zeta will be a scalar dynamics, and eta will be with the order of n minus 1 dynamics. Fine. So now we will discuss about the design of this generalized system with a single input. Okay. So to fulfill the aim that as t tends to infinity, x of t is going to be 0, we are choosing a sliding surface in the transform domain, that is s equal to zeta plus k into eta. K is a design parameter, and I will definitely mention how to choose the design parameter k subsequently. Now what is our aim? What our aim is to make s and s dot is equal to 0 in finite time. That is our objective, because if we will make s and s dot is equal to 0 in finite time, then zeta and eta also is going to be settled 0 at zeta and eta is going to be settled 0 in asymptotically, and if the zeta and eta is going to settle asymptotically, definitely the x is going to be settled asymptotically. So with this aim, what we will do now, we will see what is the dynamics of S. So to do that one, what we will do, that we will differentiate S once. Okay, so we will differentiate S once, and if we will differentiate S once, the final representation will be by this equation, where we can see that U and the disturbance has appeared. Okay, and you remember that if we are dealing with the classical sliding or the first order sliding, then at the first derivative of the objective function, that is the sliding variable, the control must appear. So this is called relative degree 1. So if the objective function you have chosen, which is relative degree 1, then only this first sliding is going to work. So that is another way to give a hint that how to construct the sliding surface. Not only it is an objective function, also you have to design the sliding surface in such a way that at the first derivative of S, the control should appear. Okay, now once this S dot has appeared, now only our objective is to stabilize this S. S dot means S and S dot equal to 0, and also we have to stabilize the reduced order dynamics. So that's why we have written the system in the coordinate of eta dot and S dot. Okay, so previously you see what was your eta dynamics. Eta dynamics was A11 eta plus A12 zeta, and from this expression we can find out zeta equal to S minus K into eta. So we have substituted that one, and then the dynamics we have represented in the form of in the coordinate of eta and S. Now we want to design a U in such a way that we can make S and S dot equal to 0, and if we make S and S dot equal to 0, then we want to study what will happen to the eta dynamics. And here the clue is that we know the maximum bound of the disturbance F. So to do that one, so we will design a U in the form of like this. So these are all the linear part, and with this linear part we have a nu, and nu is chosen as minus L plus rho sine of S. So if we have a control U like this, and if you substitute this control in the above dynamics, in this dynamics, then what will happen? This all linear part will be cancelled out, and ultimately we will have the dynamics look like eta dot is equal to A11 eta plus A12 S minus K into eta, and S dot will be minus L plus rho sine of S plus F of zeta eta into T. Now how we will show that S dot dynamics can be made equal to 0 in finite time. So for that we will take the help of Lyapunov function, and if we will take the help of the Lyapunov function, that is V equal to half S square, and where we can see that V dot is always less than equal to minus root over of 2 rho V to the power half, and if we able to prove in this form, then definitely we can say that S and S dot are going to be 0 in finite time. And once S and S dot is going to be 0 in finite time, then what will happen to the reduced order dynamics? You see, if the S is going to be 0, so this part is going to be vanished. So eta dot will be with A11 plus A12 K into eta. So now if the AB pair is controllable, it can be shown that A11 and A12 pair is also controllable. And if A11 and A12 pair is controllable, then always we can choose a gain matrix K such that we can guarantee that A11 plus A12K, this matrix will be Hurwitz. And means we can say that eta is going to be 0 limit t tends to infinity. If eta is going to be 0 at t tends to infinity, it can be shown that zeta is also going to be 0, t tends to infinity, limit t tends to infinity. Okay, and if eta and zeta both are going to be 0, then definitely we can say that the x is also going to be 0 as t tends to infinity, means we are asymptotically stabilizing the states of the system even if the disturbance is present. Now some of the very important characteristics of the sliding mode control we have to note down. What are that? Now, it is seen that during sliding mode the system is completely independent of external disturbance. However, it depends on the sliding surface parameter. So here you see, whenever we are achieving sliding motion, at that time the reduced order dynamics is completely disturbance free. Fine. And another important observation is that the order of the system is reduced by the number of control input. So what is the what is the order of the eta? It is n minus m. If we are dealing with the single input, it will be n minus 1. So definitely the order of the system is reduced by the number of the control input. The essential steps in the SMC are that designing the sliding surface such that the sliding motion dynamics is stable, and the design the SMC law to bring the sliding mode in the system in finite time. So that is very important, that S and S dot has to make 0 in finite time, and that is the essential characteristics of sliding mode control. Until the sliding manifold is reached, the control signal will be continuous. This is known as reaching phase. In this phase, the system is not robust, since closed loop system is still perturbed by disturbance. But once the sliding mode occurs in finite time, the system becomes robust against these disturbances, and the sliding mode is often called the sliding phase. So it having two phases, one is reaching phase, another is sliding phase. Now whatever the design strategy I have discussed here, let us do with an example, try to understand with an example. So now consider a system. We have taken a system that is which having A and B. Okay, and this is the disturbance D. And first of all, we have assumed that we have taken this AB in such a way that AB pair is controllable. Okay, now proceed the design SMC to the above system. How? Now we want to transform this system in the regular form. Okay, with the help of a transformation matrix, and we have taken transformation matrix T equal to this, and we have taken Z equal to Tx. So now if we take Z equal to Tx, then what we can write? Now Z dot will be equal to T into X dot, and now T X dot, we know that it is A into X plus B into U plus D. So it will be A X plus BU plus BD. So now you see it will be T into AX. Okay, T into AX plus T into BU plus T into BD. Now X, we know that here you see X is, we can write that T inverse Z. So it will be TA T inverse Z plus TB into U plus TB into D. And if you compute T inverse A, T inverse, TA, T inverse and TB, definitely they will be look like this, where you can see that only the control and the disturbance is acting at the lower dynamics. Okay, so this is called the regular form. Once you have this the equation number 6, then it is very easy to design the sliding variable that will be in the form of C transpose Z, that is C1 into Z1 plus Z2. So here we have to design the C1, that is the design parameter. So now I will tell you that how to design this C1. So now if we will make S equal to 0, whatever the steps I have shown, if you follow that one, so you will reach that Z1 dot equal to minus 5 into Z1 minus 10 into Z2, and Z2 will be equal to minus C1 into Z1, because with the control you will make S equal to 0, and if you make S equal to 0, from here we can find that Z2 will be equal to minus C into Z1. So how to choose this C1? most of the time I have seen that students are doing mistake. C1 they are arbitrarily choosing greater than 0. No, that is the wrong approach. So now the clue is that you have to make C1 in such a way that the Z1 dynamics can be stabilized. So you just put the C1 here. So if you put the C1 here, so what you can write, that Z1 is equal to minus 5 into Z1 minus 10 into, so it will be plus 10 into C1 into Z1. So now you see we can write minus 5 plus 10 C1 into Z1, and the hint is that we have to stabilize this system by choosing a proper value of C1, and it can happen only if minus 5 plus 10 C1 is less than 0. And from there we can see that C1 must be always less than 0.5. So you have to choose a C1 less than 0.5. Here for the simulation purpose I have selected that is 0.3. And now the control law will be simply minus CB inverse. Okay, so this is CB inverse into CAZ plus, that is the rho into sine of S. So now if you implement this control law, then the simulation result has been shown here, where we can say that both the states are going to be 0 as t tends to infinity, even if the disturbance is present, and sliding variable is perfectly going to be 0. And this is the control law. Here you can see that the almost 1 second time is required to reach to the sliding surface. So this you can say that this is the time, that is the reaching phase, and this is the after 1 second the sliding phase started. So that's why if you see the control law, during the reaching phase 0 to 1 second the control is continuous, but at this time the system is not robust. But after 1 second the system becomes robust, because once the sliding starts, system trajectories enters to the sliding manifold, and the stability means the robustness is achieved. Now as a summary, as I can say that if we have a system x dot t equal to a into xt plus b into ut plus d, then we can choose a sliding surface c transpose x equal to 0. And for this sliding surface, the control law will be minus C transpose B inverse CAX plus Q sine of S. Q is the gain. How you will choose the gain? Now it will be the maximum bound of the disturbance. That's why C transpose B dt. Okay, that is the modulus of that plus eta. Eta is sum greater than 0 to ensure the eta reachability condition. So now you try to think that if we want to implement this control law 9 with the sampled version of state X and S, okay, because S, you see, it is also depending on the state X. So now suppose if instead of continuous state xt, if the sample states are available, suppose xti is available, then how this control law will be designed? So using periodic implementation of this control law ut with x of ti is extensively studied in discrete mode, discrete sliding mode control, where it is observed that the SMC, when it is implemented in digital platform, exact sliding mode is not possible due to the discrete nature of the control law. So if you discretize this, if this control law is depend on the sampled values of states, it has been observed that perfectly you cannot make S equal to 0. You see here you have made S equal to 0 perfectly, which is not possible when you are going for discrete implementation. Okay, that is the first observation. It has been observed during discrete time sliding mode control implementation. Then what will happen? However, the system trajectory remains bounded in the vicinity of the sliding manifold. So instead of S perfectly S equal to 0, it will be in the vicinity of the sliding manifold. If the control is implemented at some constant sampling period, means periodically, then the bound of the sliding trajectory also depends on the sampling period. Also, it depends on the maximum bound of the disturbance, means the bound of the sliding trajectory depends on the sliding period as well as the disturbance. In other words, steady state bounds of the system trajectory depends on the chosen sampling period and the disturbance bound. So this has been observed in the discrete time SMC. But now the question is that, can there be a method to bound the steady state value in digital implementation? Means here, if we will go for the event triggering strategy, then also we will see that the perfect sliding is not possible. We will be in the vicinity of the sliding manifold, but surprisingly, the bound of this sliding manifold no longer will depend on the sampling time, because here we do not have any concept of sliding time, sampling time, because it is irregular in nature or it depends on the event. And also we will see that it is depending on, means the bound depends on the design parameter alpha, that is the event parameter basically. So once it is not depending on the sampling period as well as the disturbance bound, then the designer having the flexibility to choose the that bound of the steady state bound of the sliding trajectory accordingly. So it is the it depends on the designer. So that's why here now we are ready to define the definition of the practical sliding mode, because no longer we can guarantee that S will be equal to 0 when we are going to do for the discrete implementation, that is the event trigger strategy also. So the system is said to be in practical sliding mode if for any delta greater than 0 there exists T1 greater than 0, such that motion of the system trajectory satisfied norm of ST will be less than delta. So not it is exactly equal to 0, but the distance from the origin will be less than equal to delta for all t greater than T1, where delta is the practical sliding mode band, and the system is said to be in ideal sliding motion if we able to guarantee that ST equal to 0. So that's why if we able to guarantee that norm of ST is less than equal to delta, that will be the definition of the practical sliding mode. Okay. Then the SMC in the discrete implementation, now you see the continuous control law which we have derived here. Okay, the control law which we have derived where it is pardon, here. So the equation number 9, now it is implemented with the sample version, that is x of Ti and s of Ti. Okay, where s of Ti is equal to C transpose x of Ti. For sample data implementation, that h equal to, that is the sampling period, that is Ti minus 1 minus Ti. And if you are going for the periodic sampling, then h is fixed. Okay, but if you are going to implement this control law in the framework of event triggering, then this h is not fixed. It depends on the triggering instances or the event. So now if we want to implement this control law using event triggered SMC, then what is our objective? Now in event triggered SMC, the main objective is to design the switching gain Q such that the practical sliding mode is enforced in the system. That is very important notion. So now you can think that if I will implement this control law depending on the sample value x of Ti, is this Q will be same, the control gain Q will be same as before what we have chosen, that Q equal to norm of C transpose B dt plus eta? No. So that's why now again you have to reevaluate that what will be the switching gain Q to stabilize the system when we are depending on the sample value x of Ti, which is depending on the event. We will see that the gain condition of the practical sliding mode is not same as the continuous time sliding mode case. Okay, and following sufficient condition enabled to design first the steady state bound of the sliding trajectory, then develop the event triggering scheme to achieve this objective. So whenever you are going to design a event triggered sliding mode control, then we have to define the inter event time, that is Ti equal to Ti plus 1 minus Ti, which is aperiodic definitely. So then we have to design a stabilizing triggering rule, and also we have to show that inter-event execution time, that is Ti, which is the difference between the two consecutive sampling instance, are always greater than a positive value, because it will guarantee that avoidance of Jeno phenomena. And Jeno phenomena is that it will guarantee that there will be no infinite number of execution of event in a finite time. So these are the things you have to guarantee. Now this is the theorem which is guaranteeing that the stability of the sliding motion or event triggered sliding motion. So if we are able to guarantee that C transpose AET mod of this is less than alpha, and if we choose a control gain Q, that is you see now it is different, a alpha term is added, Q is greater than of this, then we can guarantee that the practical sliding motion is achieved. Now the question is that how this equation 13 is derived. Previously, you see that in the first lecture I told that all the event condition will come from the stabilizing condition. So now that's why we have to guarantee the stability. To guarantee the stability, we have chosen a Lyapunov function, that is half s square. And if you do the v dot, then you can see that we are live with these terms and these terms and these terms. Now, if we want to guarantee that the stability of the system, so definitely this C transpose AET must be bounded. So that's why we have taken a bound on this variable which is less than alpha, and this will play as a triggering condition, means whenever we are going to cross this bound alpha, then only the triggering will be generated and the system means the control is going to be updated. Okay, and now how we can guarantee the bound of this and this, because this is bounded definitely, because already d is replaced by d max. Now it can be observed that once the trajectory reaches to the sliding manifold, then definitely the sign of STI and sign of ST will be equal. And if you use that fact, then easily it can be shown that if you choose the Q, what the Q I have mentioned here, if you choose a control gain Q like this, then easily the sliding motion, the event triggered SMC can be guaranteed, and we can find out what will be the steady state bound of the sliding trajectory, that is alpha by norm of A. And you surprisingly you see the steady state bound of the sliding surface, it is not depending on the sampling time, because here no concept of sliding time, it is actually event. So that's why it is depending on the event parameter alpha, and it is not depending on the maximum bound of the disturbance. So now only the parameter, choosing the parameter alpha, the steady state performance of the system can be guaranteed. Okay, and we will see that this choosing alpha depends on the number of control executions also, means number of control updates also. If you take a very large alpha, then what will happen? Actually you are living with a very big region or the big bound, and once you will relax the bound, then what will happen? The number of control executions will be less. If it is less, and then if you use a larger bound, definitely the system performance will be, you will lose the system performance. And if you choose a very less alpha, then it means that you are allowing a very strict condition, and the region is very small to evolve the ST. So now if you choose a very small alpha, then definitely number of control updates will be more, but your system performance will be better compared to the earlier ones. Okay, so now thing is that that's why once the trajectory remains within this region alpha by norm of A, once it enters the band, therefore the sliding trajectory remains bounded within a band that is dependent only on the design parameter alpha. This ensures the practical sliding mode in the system, and the proof is now completed. Fine. Now we have shown that sliding mode will be achieved in finite time, but we have not shown the system stability. We have to show, because here the AS is not going to 0 in finite time. Sorry, AS is not going to be perfectly 0. It is going to be inside a band. So it is our work to show that what will happen to the system stability. So that's why here it has been pointed out that as a remarks, the value of alpha determines the steady state bound of the system trajectories. Hence, it must be chosen to satisfy the design constraint. That already I have discussed. It is always possible to provide the upper bound on alpha that guarantees satisfactory performance of the system. However, for large values of alpha, large steady state bound is obtained with minimum computational burden. Okay. So now, as I told you that as the AS will be inside a bound, then definitely we have to show what will happen to the reduced order dynamics. So to do that one, again we have represented the system in regular form, and then we can find out that the reduced order dynamics will be now governed by the equation number 19, where we can see that a extra term is present, that is A1 to S. Fine. So now, how can I guarantee that xt will be stable? So now here you have to you have to consider that no longer we can assure that x1 is going to be 0 as t tends to infinity. We can maximum guarantee that x1 norm of x1t, okay, will be bounded by a region, means we can guarantee that uniformly ultimately boundedness of the system trajectory. So that's why it is a linear system. So that's why we have taken a Lyapunov function in the form of x transpose px. You see, that is the x transpose px, x1 transpose p x1, because we are going to derive the stability condition of the system state x1, and we will do the v dot, and if you do the regular calculation, it can be shown that xt always will be bounded by this value, that is 2 alpha norm of a1 to transpose p by lambda mean of phi, that is norm of a. So this is the bound in which, or this is the radius of the ball inside which the x1 will be also. So here we are giving the notion of, or utilizing the notion of, ultimately boundedness of the system trajectory. So it is the notion of the practical stability. Now this is the triggering rule. You see that from the condition what we have achieved to guarantee the stability of the sliding motion, that is S, and we got this will be the triggering condition, and also we can say that the next triggering instant ti plus 1 will be generated only when the violation of this triggering condition. So this is has been done, and the next thing is that only you have to show that the inter-event execution time, that is ti, that is ti plus 1 minus ti, always will be greater than a positive value. Okay, so for that, what we have to do now, we have to see that maximum growth of the error, means det by dt. So det by dt we have computed, and we have seen that from there that always these are the required calculation you have to do. I am avoiding this calculation because only the notion is important, that what you have to do, that notion is important, and why it has to be done, that is important. The calculations you can do definitely when you will get the off time. So after doing some calculation, it can be shown that always the TI, the inter-event execution time, will be bounded by a positive value. That is also has to be guaranteed whenever you are dealing with any event triggered control strategy. You have to ensure the stability. From the stability condition, you will arrive with the event condition, and once the event condition is generated, then with that event condition you have to guarantee that inter-event execution time is always bounded by a positive value, and that will guarantee that the avoidance of the Geno phenomena. What is Geno phenomena? Now here actually it can have, it is here we are doing the sampling not based on time, it is based on event. So it can happen that in a finite duration of time, infinite number of event may generate. To avoid that fact, always we have to guarantee that the inter-event execution time will be bounded by a positive value. So now we have in fact simulated a system x of t equal to 0, 1, 4, 5 xt. So this is a linear system with a disturbance, and it has been observed that both the states are converging to 0, but here actually they are inside a band. If we zoom it, you can see it, and which is visualized in the sliding surface. Sliding surface is not exactly 0. Instead of that, it is inside a band, and this band size depending on the alpha. If you choose a very large alpha, then definitely this band size will be larger. But if you have the larger band size, then you will get a poor performance. But in terms of control update, you will be saved. At that time, number of control update will be less. Okay, so this is the control input. It is discontinuous in nature, and this is the inter execution time. Here you can see this. You can see that it is sparsed, which is obviously sparsed from the that is periodic implementation. Okay, so now some discussion we will make. So alpha must be selected to incorporate practical constraints. Okay, if tau min, which is the minimum value of the inter-event execution time, represents the minimum time for control execution, then alpha should correspond to Ti, which is greater than alpha min. And we have also found out the triggering rule, which is depicted in this equation, so which demands the continuous state measurement. Thus it needs the dedicated hardware. Okay, so here we need a continuous measurement of the states, because here you can see that it is depending on E, and E is depending on x of t. Fine. So that's why we need a continuous measurement of states. So that's why to check this condition, event condition, we need a dedicated hardware. Okay, and that's why from here the research has been started that that if we do not have the information of x, then how we can evaluate this event condition. Okay, can we do, or can we check this xt periodically instead of measuring it regularly? So these are the things are important for the future research. Okay, so as a conclusion, in event triggered SMC, the steady state bound can be designed as per any desired value. That robust system performance is also achieved. The system strategy, this strategy can be extended for the nonlinear system. So here I have shown you for the linear system, then this concept also can be extended for the nonlinear system, and there are many research is going on, particularly in the event triggered sliding mode control. Okay, here you see I have not considered any network induced constraint like delay, packet loss. So if you consider that imperfection of the network, then how the event triggered SMC can be designed. So all these issues are there by and which are very current research trend in this area. So those who are interested, they can start with this book, which is written by Professor Bandyopadhyay and Bera, that is Event Triggered Sliding Mode Control, a New Approach to Control System Design, Springer, which is published in 2018. So if you want to start to have a look on the event triggered sliding mode control, you can start with this book. And if you want to learn the sliding mode control, then you can go for the reference number 3 and 4. They are very good book to understand the sliding mode control. That is Spurgeon, Edwards and Spurgeon, and the sliding mode control and observation by Stachel, Edward, Friedman, and Levant. And this presentation I made from this 2, 3, and 4. Also, I am heavily influenced by the slide presented by Professor Bandyopadhyay in IEEE IES distinguished lecture presentation, that is event triggered sliding mode control. So these are the very important references which you can consult if you are interested to start the research in this particular domain. Okay, so with this I will end here.